Good morning. In the previous class, we discussed about numerical solution of initial value problems governed by first order ordinary differential equations, and we also discussed about Taylor series method for solving such a first order differential equation in which an initial condition is specified. So, let us recall Taylor's series method of order n and then use this method to solve some initial value problems and illustrate the method. So, we said that if we have an initial value problem governed by dy by dx is equal to f of x comma y in the interval a to b, subject to an initial condition y of a equal to y naught, and suppose that the solution y of x to this initial value problem has n plus 1 continuous derivatives, then we can expand the solution y of x in terms of its nth Taylor polynomial about the point xi and evaluate y at the point xi plus 1, which is xi plus h. So, y of xi plus 1 will be y of xi plus h y dashed of xi plus h square by factorial 2 y double dashed of xi plus etc. plus h power n by n factorial into nth derivative of y at xi plus the error term, which is of order of h power n plus 1, since we want to use Taylor series method of order n, and psi I belongs to the interval xi to xi plus 1. So, here the various order derivatives of y which appear in this expansion are obtained by taking derivative of the right hand side function f of x comma y. So, the successive derivatives are presented in terms of the partial derivatives of different orders of f with respect to x and y. So, when we compute the derivatives of y with respect to x of several orders, namely up to order n is what we require to write down the solution at xi plus 1, then we have Taylor series method of order n given by y of a is y naught, that is the initial condition. Then when we know, we can compute y1 with I is equal to 0 by substituting the derivatives evaluated at the point x naught comma y naught. When we know y1, then we use this expansion to obtain solution at x2, namely y2, and continue till xn at which we require the solution, which is denoted by yn, which approximates y at xn. The local truncation error is of order of h power n plus 1. So, we had derived this method in the previous class and we have just recalled what the method is. So, let us consider some examples and then see how we can apply this method to the solution of initial value problems governed by first order differential equations. So, let us take dy by dx to be y minus x square plus 1 in the interval 0 to 2, initial condition is y of 0 equal to half, and say we are asked to get the solution by Taylor's method of order 2 and 4. So, we require derivatives of y up to order 4. So, let us take y prime, which is y minus x square plus 1, and compute the successive derivatives, and then we can evaluate these derivatives at the initial point. So, y prime at 0 is y of 0 minus x square where x is 0 plus 1. So, that gives you 3 by 2. Then y double prime 0. So, we substitute the values of y at 0, x is itself 0, and so we get this to be 3 by 2. So, similarly, we evaluate the third order derivative at the initial point, the fourth order derivative at the initial point, and keep these values ready, and then take the step size to be h is equal to 0.2. So, let us take h to be 0.2 and then obtain the solution. So, y at 0.2 will be y of 0 plus h y dashed of 0. Since we want to use Taylor series method of order 4, let us compute the solution with order 4 first. So, we have terms up to h power 4 by factorial 4 into fourth derivative, and we already have these values computed with us. So, substitute, then you end up with a solution that y at point 2 is 0.8293 by Taylor series of order 4. So, now let us compute the solution using Taylor series method of order 2. So, we just require terms up to order of h square in the expansion, and we already have these values. We substitute and we get this value to be equal to 0.83. So, we have solutions y at point 2 using Taylor series method of order 2 turns out to be 0.83. So, let us see what the exact solution is. The exact solution is x plus 1 the whole square minus e power x by 2, and this can be immediately verified by computing the derivative y prime. So, since I have computed the solution at point 2, I evaluate y at x, which is 0.2. So, substitute x as 0.2 and that gives you y at 0.2 to be 0.8293, and this is correct to 4 decimal places. So, what is the actual error when we use second order method? The solution computed numerically is 0.83. The exact solution gives 0.8293. So, the error that is occurring in this computation is 0.0007, whereas at this point when we require solution correct up to 4 decimal places and use Taylor's method of order 4, we see that the method of order 4 and the exact solution match up to 4 decimal places. So, we are required to compute the solution in this interval 0 to 2 by taking step size to be 0.2. So, we have worked out the details by computing the solution at 0.2. So, now solve the new initial value problem, which is dy by dx is equal to y minus x square plus 1, subject to the condition that y at 0.2 is 0.8293 by Taylor series method of order 4. So, we have a new initial value problem. So, we would like to march one step ahead. Since h is 0.2, we will compute the solution at x is equal to 0.4 and obtain y at 0.4. And we continue this process till we reach the end point of the interval, and the end point of the interval is x is equal to 2. So, we can march step by step with a step size h is equal to 0.2 and determine the solution by Taylor's method of order 4, and similarly use Taylor's method of order 2 and compute the solution at discrete points which are equally spaced with step size h is equal to 0.2, and move on up to the end point of the interval 2 and determine the solution. And since we march at any time one step ahead to determine the solution of the initial value problem, we say that this method is a single step method. In addition, it is also an explicit method, because if we know the solution at yi, then we compute the solution explicitly at the point xi plus 1, namely if we know the solution at xi, which is yi, then we compute the solution at the next point xi plus 1, which is yi plus 1. So, we also call this method as an explicit method. So, it is a single step explicit method which can be used to solve the initial value problem governed by first order ordinary differential equation, and depending upon the accuracy that we want, we can include as many terms as we want, so that the desired degree of accuracy is reached. So, let us consider another example. So, I want to solve this time the differential equation dy by dx is equal to x minus y square, initial condition y of 0 equal to 1. So, Taylor series for y of x, because initial point is 0. So, Taylor series for y of x will be y of x minus 0 plus 0. So, it is y of 0 plus x y prime 0 plus x square by 2 y double prime 0, x cube by 3 y triple prime 0, and so on. Depending upon the number of terms that we want to include, we can consider these terms. So, let us compute these derivatives. We see that y prime, y double prime, y triple prime, etc., say up to 5th derivative have been computed. and the values of these derivatives at 0 also have been computed. So, that y prime 0 is minus 1, y double prime 0 is 3 and so on. So, the values of the derivatives are also evaluated at this point. So, we write down at any x the solution is given by y of x is equal to 1 minus x plus etc., where x is greater than 0 because the initial point is x is equal to 0. So, starting from 0 we march ahead and then determine the solution by this method. Or if you want to go march backwards and get the solution say at minus 0.2, minus 0.4 etc., that can also be done using this expansion y of x is equal to 1 minus x plus etc., which is given by this. Now, the question is, suppose we want to compute y at 0.1, taking the step size h to be 0.1, right, and determine the solution correct to 4 decimal places at that point. So, we do not know how many terms we have to add in the Taylor series. So, to begin with, I take the first 3 terms. I can start with any number of terms to begin with. Let me start with the first 3 terms, which is 1 minus x plus 3 by 2 x square, and compute y at 0.1. So, I substitute these values and determine y at 0.1 to be 0.915. Alright, since I want a solution correct to 4 decimal places, let me use a Taylor series method of order 3 now. Namely, I include the next term and then substitute x is equal to 0.1 and evaluate y at 0.1 by taking x as 0.1. Then I end up with a value which is 0.91366667. So, with the third order method it is this value. With the second order method the value of y at 0.1 is 0.915. I observe that they differ even at the third decimal place. So, I cannot stop. So, I have to compute, and so I consider the Taylor series method of order 4. So, I include the 4th order terms also. Already I have computed the solution by taking into account up to 3rd order terms. So, I know the value. I simply have to add the 4th term and evaluate it at x is equal to 0.4. When I do that, I see that it is 0.91380834. When I round it off to 4 decimal places, this gives me 0.9138, that is from the 4th order method. Whereas, by a 3rd order method, I obtained this solution, which when rounded off to 4 decimal places will be 0.9137. So, they do not match at the 4th decimal place. So, I cannot stop, and so I will have to add say another term and check whether I get the desired accuracy. So, I write down the solution y of x by incorporating terms up to order of h to the power of 5. So, I have the values up to this by my previous computation. I only have to add this term to it, and when I do that I end up with this solution, and I observe that correct to 4 decimal places this gives me 0.9138, and correct to 4 decimal places the solution obtained by adding just the terms up to h to the power of 4 also gave me 0.9138. So, by including the 5th order term, right, I am able to get a solution which matches with the previous solution obtained by Taylor series method of order 4 correct to 4 decimal places, and therefore, my solution is 0.9138 correct to 4 decimal places, and this is obtained by using terms up to x to the power of 4 in the Taylor expansion. So, now suppose say I would like to check up to what values of x can I use just Taylor expansion up to terms containing x to the power of 4 such that the solution that I get from that will be correct to 4 decimal places. So, is that solution valid for all values of x, or up to what values of x is it going to be a solution which gives me the desired degree of accuracy? So, we look at the error term and say that the error must be such that it should be less than, right, 0.4 zeros followed by 5, because I want the solution correct to 4 decimal places. So, what is the neglected term? The neglected term is the term containing x to the power of 5, because the term up to terms containing x to the power of 4 have been taken and the solutions have been obtained at point 1, and we have been able to satisfy our requirement, that it satisfies the desired accuracy. Namely, we have been able to get solution correct to 4 decimal places. So, let us see for what values of x is this correct, which means the neglected term, namely the error term, must be less than or equal to 0.4 zeros followed by 5. So, this gives you x must be less than or equal to 0.126. So, all values of x up to 0.126, wherever you want to obtain solution using Taylor series expansion of order 4, you will get your solution correct to 4 decimal accuracy. That is what this information gives us. So, this is one way of approaching, namely making the Taylor series method to be of higher order, so that incorporating more and more terms and then checking whether the solution obtained by a method of order n plus 1 matches with the solution obtained by using a method of order n correct to the desired degree of accuracy. Then one can also do the or one can also compute the solution by taking the step size to be smaller and smaller. Here we have taken h to be 0.1 and then evaluated the solution at 0.1 by using different Taylor series method, namely Taylor series method of order 2, order 3, order 4 and so on, and then we stopped only when the desired degree of accuracy was attained. On the other hand, we can choose a smaller step size h. Instead of h as being taken as 0.1, start with h to be equal to say 0.05 and check whether your solution obtained by Taylor series method, say of order 2 or of order 3, gives you the solution at x is equal to 0.1 correct to the desired degree of accuracy. If it is not, reduce your h further and then work out the details step by step and then finally obtain the solution at 0.1 and check whether your desired degree of accuracy is attained. So, that is another way of approaching the same problem, namely reducing the step size h or taking the step size h to be very small and then checking out the solution at the point at which we desire the solution, and then if it is satisfied, we stop our computations. That is one approach. The other approach would be to take Taylor series method of different orders, take the step size h to be say 0.1 and then compute the solution at 0.1 by different Taylor series method of different orders and then check whether our accuracy is attained at some stage, right. So, let us now consider another example. So, given this initial value problem, dy by dx is equal to x square plus y square, y of 0 is equal to 0, we determine the first non-zero terms in Taylor series for y of x and hence also determine x when the error in y of x is obtained from the first 2 terms which are non-zero should be such that it is less than 10 to the power of minus 6 after rounding. So, there are 2 parts to it. One is take the first 3 terms in Taylor series for y of x and obtain the value of y at 1. So, let us first look into the details. The initial point is 0. So, we expand Taylor series about 0. So, we require the derivatives to be evaluated at 0. So, we first compute the derivatives. So, y prime is f, that is x square plus y square, but y prime at 0 is 0, right. So, the first term, how does it look like? Y at x plus 0 minus 0, which is y of 0 plus, right, x into y prime 0, that y prime 0 turns out to be 0. So, we essentially have only one term which is y of 0, and what about that? y of 0 is given to be 0. So, if we have a Taylor series method of order 1 y of 0 plus h y prime 0, then we essentially have nothing on the right hand side, because y prime 0 is 0, y of 0 is also 0. We compute y double prime, and that evaluated at 0 also turns out to be 0. So, terms up to order of x square all vanish. So, we go to Taylor series method of order 3, compute y triple prime 0, that turns out to be non-zero. So, this is the first non-zero term in the Taylor expansion, right. So, we get a non-zero, we can get a non-zero value of y at any x by using a Taylor's method of order 3, so that the contribution comes from y triple prime 0 and it is a non-zero value. So, we move ahead, compute y fourth derivative at 0, that turns out to be 0, the fifth derivative, the sixth derivative also turn out to be 0. So far we only have one non-zero term coming from this y triple prime 0 into h cube by factorial 3. So, we compute the seventh derivative and evaluate it at 0, we see that it is a non-zero quantity, namely 80. So, we have the second non-zero term in our Taylor expansion. So, all along we have considered terms up to h power 7 by factorial 7 into seventh derivative at 0, which is non-zero. But on the whole we have only two non-zero terms in the Taylor expansion. We go ahead because we are asked to take the first three non-zero terms, right, in the Taylor expansion. So, we go further ahead to compute the next non-zero term. We observe that the ninth derivative is at 0 is 0, the 10th derivative at 0 is 0. So, we compute the 11th derivative and evaluate it at 0, and that turns out to be this, which is 38,400, which is non-zero. So, we write out what y of x is using these first three non-zero terms, which is nothing but x cube by factorial 3 into y triple prime 0 plus x power 7 by factorial 7 into seventh derivative of y at 0 plus 2 by 2 plus h power 11 by 11 factorial into 11th derivative of y at 0. So, that gives you the value, that gives you the solution of y at any x. So, we want the solution at 1, that is the problem. Take the first non-zero terms, the first three non-zero terms in Taylor expansion, obtain y at 1. So, we evaluate y at 1 and that turns out to be, say, this quantity. So, we have completed the first part. The next part says, determine the values of x when error in y of x obtained from the first two terms, which are non-zero, to be less than 10 power minus 6 after rounding. So, what does it say? It says use a Taylor series method and include up to the first two non-zero terms in it. Whatever be the error that is incurred in the computation should be such that that must be less than 10 to the minus 6 after rounding. So, we only are asked to take the first two terms. So, the third non-zero term in our expansion is the first neglected term, which contributes to the truncation error. So, what is y of x? It consists of these three terms. So, we are asked to include the first two terms. So, this term will be the third term which contributes to the truncation error. So, the local truncation error will be 2 by 2079 into x power 11. So, I would like to find out the values of x for which, if I include the first two terms alone in computing the solution at any point, such that the local truncation error is going to be less than 0.5 into 10 to the minus 7. So, I compute values of x for which this condition is satisfied and we see that x must be less than 0.041. So, for all values of x take less than 0.041, you can use the Taylor expansion only up to these two terms, namely x cube by 3 plus x power 7 by 63, and write down the solution of this initial value problem which we have considered, such that the error will be less than 10 to the minus 6 after rounding. So, we have been able to get the value of x in this case to be less than 0.41. So, for all these values of x, the required accuracy will be obtained by just including the first two non-zero terms in the Taylor expansion. So, we have been able to illustrate Taylor series method by some examples above. So, we move on to the next method for solving initial value problems governed by first order differential equation. So, we consider a well posed initial value problem governed by the first order equation dy by dx is equal to f of x comma y of a is y naught, and we want to determine the solution in the interval a b. So, what should we do in a numerical method? We should divide the interval a to b into n equal subintervals of width say h by means of points xi which are given by a plus ih for I equal to 0 to n, such that x naught is a and xn is going to be b. So, let us use Taylor's theorem to derive Euler's method. Suppose say y of x, which is the unique solution to this initial value problem, has two continuous derivatives on the closed interval a b, then by Taylor's theorem we know y at xi plus 1 is y of xi plus xi plus 1 minus xi into y prime of xi plus xi plus 1 minus xi the whole square by 2 factorial into y double prime at xi I for some number psi I which lies between xi and xi plus 1. So, this xi plus 1 minus xi is the step size h. So, I substitute that and then we see that y at xi plus 1 is y of xi plus h y dashed of xi plus h square by 2 y double prime at psi I. So, since y prime is f, I can substitute for y prime here as f. So, we have this method. What does Euler's method do? Euler's method constructs an approximation for y of xi, call it yi at the point xi for each I which takes values 1 to n by deleting the remainder term. What is the remainder term? This is the remainder term. So, I delete this term and write down the resulting method. So, what is Euler's method? The initial condition given by y naught equal to y of a, and after deleting the error term, the method gives you yi plus 1 equal to yi plus h into f of xi comma yi for I is equal to 0 to n minus 1. When I is 0, you have the information that y at x naught is y at a, which is y naught. And so, if you put I equal to 0, you will get y1 to be y naught plus h f of x naught y naught. Once you get y1, y2 obtained by taking I is equal to 1 is y1 plus h f of x1 y1. So, continue this way till you reach the last point which is xn, namely b, so that it is yn is equal to yn minus 1 plus h into f of xn minus 1 yn minus 1. And you observe that Euler's method agrees with the Taylor series method of order 1. So, error in Euler's method is of order of h square. And Euler's method can also be derived by another way, namely I take the differential equation dy by dx is equal to f of x comma y and the initial condition we want to obtain the solution in the interval a to b. So, I integrate both sides with respect to x between x naught and say x1. How do I get this x1? I divide the interval a b into number of smaller subintervals by means of points xi, where xi is x naught plus ih. I runs from 0 to n. So, I start at x naught where the initial condition is given. I move to the next point which is at a distance of h units from here, call it x1. So, I integrate the given differential equation between x naught and x1. So, it is dy by dx into dx. So, that will give you y between x naught and x1. So, it is y1 minus y naught, and that is equal to integral of the right hand side, which is x naught to x1 f of x comma y dx. So, we assume at this stage that we want to approximate f of x comma y by a constant polynomial, namely the value of the function at x naught comma y naught. So, take f of x comma y to be f of x naught comma y naught in the interval x naught to x1. So, we end up with y1 minus y naught equal to f of x naught y naught into x1 minus x naught when we perform the integration. But x1 minus x naught is h. So, we have y1 equal to y naught plus h into f of x naught y naught. Once we know y1, I move on to y2. What is it? It is y1 plus f of x1 y1. How do I get it? I integrate the differential equation between x1 and x2 and use the initial condition as y at x1 is y1. So, I can get y2 immediately as y1 plus f of x1 y1. So, move ahead similarly and till you reach xn plus 1, at which the solution is yn plus 1 given by yn plus h f of xn comma yn for n running from 0, 1, 2, 3. So, that you end up with the solution at all the points starting from x naught, you got at x1, then at x2, x3, etc., xn, and now you have gone to the point xn plus 1 at which the solution is given by this. So, you observe essentially that Euler's method is Taylor series method of order 1, and therefore, what can you conclude about Euler's method? The process will be a very slow process. You require smaller and smaller values of h to obtain desirable accuracy, and the method is not suitable for any practical use, because the process is a very slow process and it requires the step size h to be very, very small, and lot of computational effort is needed to get the solution correct to the desired degree of accuracy, and therefore, it is not suitable for practical use. However, the method is a very simple method to derive, number 1, and secondly, it can be illustrated to use the techniques that are involved in the construction of more detailed methods which we consider later on. We shall now illustrate Euler's method by means of some examples. So, let us take y prime to be minus y of 0 equal to 1, and the problem is to determine y at point 0.4 taking step size h to be 0.01. So, y of 0 is given to be 1. What is y1? It is y of 0 plus h into f of x naught y naught. So, it is y naught which is 1, h is 0.01 into f of x naught is 0 and y naught is 1. So, I substitute for f of x naught y naught as f of 0 comma 1, and what is its value? F of x naught comma y naught is minus y naught, because f of x comma y is minus y. So, it is minus 1. So, I substitute here and then simplify, and I end up with the value of y at 0.01 as 0.99. So, now I go to the next step, namely compute y at 0.02. It is y1 plus h of f of x1 y1. So, I feed in those values. F of x1 y1 is minus y1. So, substitute and simplify, you get the solution at 0.02. Proceed this way and you get the solution at 0.03 and finally at 0.04 as this. So, when it comes to Euler's method, we observe that it is a Taylor series method of order 1. There was no need for computing any derivative. The derivative which occurred there was the first order derivative. We replaced it by the function value, namely f of x comma y. So, this suggests, can we develop single step methods which do not involve the computation of the various order derivatives as required in Taylor series method of order n, but it involves the information about the function f of x comma y at a number of intermediate points, say xi to xi plus 1, when we march from xi to obtain solution at xi plus 1. Namely, let us take a number of points between xi and xi plus 1 and evaluate f at these intermediate points. F of x comma y represents the slope dy by dx. So, let us consider slopes just not at xi comma yi, but at a number of intermediate points between xi and xi plus 1, and take a linear combination of these slopes and then see whether we can develop methods which are single step methods, so that our computation does not require evaluation of the derivatives, but it only involves evaluation of certain function, namely f of x comma y at some points. The answer is yes, and such methods were developed by Runge and Kutta, and they are referred to as Runge-Kutta explicit methods. So, in the next class we shall discuss these single step explicit methods which are developed by Runge-Kutta and known as Runge-Kutta methods.